Okay, in this video I would like to very briefly talk about the radial flow groundwater governing equation, and I won't talk I don't want to go into details because technically in many at least big scale groundwater problems, technically we discretize the space domain into several cells and layer, which are all made in a Cartesian system or in a Cartesian form. And if you remember that, this is exactly what we did in previous sessions with the confined and non-confined aquifer. And if you remember that, the control volume that we used to derive the governing equation was a cubic system like this, which would be actually one of these cells. So everything that we had, all the governing equations that you saw in the previous sessions were in the Cartesian system, which we usually, most of the time, we use that type of coordinate system to model our groundwater flow problems. But you as a groundwater modeler, you need to know at least what are the differences between these two form of flow. I mean the Cartesian flow, groundwater flow in the Cartesian system and the groundwater flow in the radial system. And technically, if you need to go and convert your model and solve the problem within an appropriate coordinate system. But at least in this session, I would like you to show you that what are the main differences between these two types of flow. And as you can guess, if this is my ground and if we have a well like this within a confined aquifer, and if the well is fully penetrated and is screened all across the B thickness of the aquifer, so it is fully penetrated because we would like to assume a depth average concept. Okay, so all the water will flow parallelly like this, but from the surrounding space. If this is the plan view of the well, so technically if this is a pumping well, so technically the water moves toward the well radially like this. Okay, and what happens here, how the head changes within a radial system, usually if this is, for example, our initial condition or initial groundwater head before pumping, it is above the confined layer because this is the confined layer. So if this is the head profile, and if we start pumping groundwater out, technically what happens, the groundwater head, which was here, it starts to drop and the cone of depression starts to propagate. For example, at first it is like this, and if you keep pumping, eventually it will go and reach into the state condition. Okay, but how we can go and derive the governing equation, technically everything is pretty much the same, but now the main difference comes from the control volume. So if I want to draw the control volume, I don't know why I cannot control the pen. So if I want to draw the control volume, now my control volume will be actually, if I want to look at from the top, if this is my well, so technically I have a technical problem, I guess. So my control volume, this does not look good, so let me go. the control volume is actually a cylinder like this. This is what you see from the top. From the side, technically if this is the well, so this is my control volume. So technically this is the control volume around the confining layer. So technically this is my delta R. My R0 is here, so this is my RWR well, and this is my R. Okay, so technically if I do the mass in minus mass out equals accumulation calculation, and use the Darcy's law within a radial system, which is QR negative K partial H partial R, I should be able to go and calculate the governing or derive the governing. I don't want to go and derive the governing equation again here, but I will just write it down here. But think about this and go and look at the textbooks. And actually, it's a very good, that would be a very good test questions. So you can go, so let me write just the governing equation here. So the governing equation would look like this. The second derivative of 5 with respect to R plus 1 over R partial 5 partial R equals ST, transmissivity, partial 5 partial T. Okay, and the T is actually K times B. So so what does it mean? That was the governing equation of groundwater flow within the radial system. Let me write it down again here. Let me correct. Anyway, so if I want to write the governing equation here again, that is partial phi partial R square over 1R partial phi partial R is T partial phi partial T. And as you see here, the solution of this equation is phi, which is the groundwater head, at any distance from the well at any time t. So this is the transient solution of this partial differential equation. And as you can see, you can say that, actually you can guess that this governing equation is valid at R greater than W. So if this was the well, so this was the radius of the W. So we are interested to find how the head distributes within this space from RW to the boundary condition that actually we are looking at. And as you see here, this is a second derivative with respect to R. So it says that to solve this problem, you need to have two boundary conditions, and because of this, you need to have an initial condition. Okay, so people went and mathematicians actually went and solved this problem, at least for very basic boundary condition and initial conditions. For example, if this is my confined aquifer, and if this is my well, I know that, for example, they assumed that at the very beginning, at the initial condition, the head profile of the confined aquifer is flat line like this. Okay, so it is above the upper confining layer because this is a confined system. So this is the initial condition, okay, which is a flat line. So technically the phi at any r at time 0 is a constant number, phi 0. So, and this is my RW, and this is R, which goes to infinity. Okay, for example, it can go to infinity. So after we pump water out of the system, sorry, so we denote it with Q or QW. QW. We know that the head at the well, which was there, so it starts to drop and the cone of depression starts to propagate. So it goes here, and eventually if you keep pumping for a long period of time, the system will eventually reach a steady state, and this will be the cone of depression. Okay? So to solve this problem, mathematicians actually solve this problem by rewriting this equation differently. And in a minute you'll see that that was a very brilliant idea, because that helped them to solve this partial differential equation. And what they did, they converted everything here, which is based on the groundwater head changes, phi. They changed this to the concept of drawdown. What is drawdown? Drawdown is actually, so let me erase this. Oops. So the drawdown is actually this distance, the amount of head that we have lost at any point with respect to the initial condition. So this is the drawdown. Okay, and physically it is nothing but, so they usually show it with small s. So it is nothing but the initial condition, phi 0, minus the phi at that time, right? So this is the phi, the groundwater head, at that specific position at that time, minus, if I subtract it from the initial condition, I can find this distance, which is called drawdown. Okay, so if this is the equation, I can go and make the derivative with respect to r from both sides. So technically, if I make derivative of s, the small s, okay, with respect to r, this equals with, so this is constant, so this will be 0, so this will be equal to partial phi partial r. Okay, so this is the beauty of a partial differential world, actually. So if I keep going and find the second derivative of the drawdown, this will be partial phi partial r, right? And simply I can do I can find the derivative of s drawdown with respect to time. Okay, which will be partial phi partial t. So, but please be careful that actually this s is the drawdown and it is different from this s. So this is actually capital S. This is the storage coefficient. Okay, so this is a constant number. Okay. Anyway, having these, if I go and substitute these three equations into the governing equation, then I can rewrite the governing equation based on the drawdown. So technically I can define a drawdown partial differential equation. Okay, so let me write the drawdown equation here. Okay, which this guy is actually a function of time and position, and this guy itself is a function of r and time, right? This is a constant number. This is the initial condition. So if I substitute these equations into this governing equation, then I can write the drawdown partial differential equation. Okay, plus 1 over r plus s plus r equals capital S t partial s partial t. Okay, so you wonder why they did this, because it pretty much it looks like the same as this equation, right? But what happens here, once you convert phi into s, you can define a boundary condition and initial condition such a way that it allows you to use mathematical techniques to go and solve this equation. That's why they did this. So for this equation, for example, the boundary condition, if this was okay, so if this was the well, so this is the initial condition and this is the drawdown. Okay, so the initial condition for this problem can be written as at time equals to 0, s at all r's, which are from rw actually, which are from r is r is greater than rw and less than positive infinity, for example. Okay, so the initial condition can be written as at t equals 0, the s at all r but at time t is 0, right? So because this is phi 0, phi 0 minus phi 0 is 0. So this is the initial condition. Beautiful 0. Okay, so the boundary condition 1 at r infinity. So if you go far enough from the well, technically you can go and say that the s at r which goes to infinity, or let me r at infinity, sorry, the s at infinity at any time t, is again 0. Okay, so you can see it here. And boundary condition 2 can be written as at r equals r dot w, at t equals 0, the q w is 0, the amount of the pumping rate actually. The pumping rate is 0, but at t greater than 0, immediately q goes to a constant, the Q becomes, the QW is, sorry, let me write it this way. So the QW is, the Q is 0, but at T greater than 0, the Q equals QW, which is a constant value, constant pumping rate. Okay, so having these initial condition and boundary condition, they went and solved this problem. Okay, but don't get confused with this concept of R as R which goes to infinity. So this is a mathematical infinity that would be that would have a different meaning, or so let's say it this way: the R, which if goes to infinity, mathematically it means that the R, so we are far away, far enough from the well. That would be, for some cases, that R infinity can be considered as, for example, 100 meter, greater than 100 meter. That in some cases that would be, I don't know, like 10,000 meter and so on. So this is a different concept, actually. So don't get it confused with the abstract infinity concepts that we had. So they went and solved this problem, and they found the solution as this. So let me write it here. So the solution, the drawdown at any space, at any position R, at any time T, was calculated as QW, the constant number that we had at the well, 4 pi T integral of U to infinity E minus U du. Okay, where the U that you see here itself is a function of R. This is the sortivity, the capital S, constant number, for T transmissivity times T. So this itself is a function of time and R. This was the analytical solution or closed form solution for that radial problem that we had. Okay, but solving this integral is not easy. So technically, you have to go and numerically solve this problem. Okay, but they went and approximated this problem and find a series form solution for this integral, and they denote it as WU. Okay, so technically, if I want to write the analytical the solution again here, they said that the S at RT equals QW 4 pi T WU. Okay, and what is this WU? I wrote it in the next slide, that you see that actually they went and calculated the WU, which you'll see in the next slide. By the way, this function has a name, and in the textbook they call it well function. Okay, so it is a very well-known function, at least in groundwater hydraulics textbook. So the WU can be approximated using this formula. W equals to negative 0.577216 minus natural log of U plus U minus U squared to 2 times 2 factorial plus U raised to the power of 3 times 3 factorial minus u raised to the power of 4 over 4 times 4 factorial, and so on. Okay, so this is actually a series form solution for wu, and if you have the wu for your u, which itself is a function of r and time, which equals with r squared times storativity over 4t times t, you can go and find the drawdown at any distance from the well and at any time t, which is the transient solution of this equation. Okay, let's go solve an example problem, and I believe things will get more clear. For example, the problem is I want to find the drawdown at distance r, which is 124 feet from the well, at time 100 minutes, and at the transmissivity is 1400 feet square per day, and storativity is 2.4 times 10 negative 5, and the QW is 42,400 cubic feet per day. First, I need to go and find u. If you look at the u equation, it says r squared is 4t, so the u is r squared s 4t lowercase t. So technically this is the r squared, this will be 824 to the power of 2 times the s is 2.4 times 10 to negative 5, and this is 1400, and you need to be careful and convert everything to the you need to be consistent with the unit. So let's use everything in terms of day. So this will be 100 minutes times, if I want to convert it to day, that will be 24, which equals to 0.042 or 4.2 10 to negative 2, right? So I have calculated, so this is my u that I calculated. If I plug in u into this equation, I can go and find the WU of 4.2 10 to negative 2 using this equation that I have, and if I do that, my du will be almost 2.68. Okay, now I have my WU. Now I can go and find the drawdown at 824 feet at 100 minutes. Okay, as so what was the formula? So the formula was Q. So the Q, the value of Q is 4,000 cubic. So let's put the units, cubic feet per day. 4 times pi times T, okay, which is cubic feet per day, times WU, which is 2.68. Okay, so if I do that and if I go and calculate that, it will be 6.45 feet. Okay, so technically this way you can go if technically, for example, if you have a well in a confined system, so, and if you know how much you're going to pump out, you can go and find the drawdown at any points from the well at any times t. Okay, so technically you can go and find the drawdown first and convert everything into the phi if you're interested to. Being a fully penetrated well. So I will stop here, and I don't want to spend more time and talk about the radial flow, but what I want you to learn in this class is that I want you to know that the radial flow system is totally different with the Cartesian flow, and the governing equations are different, and technically it is a little bit much more complex, but it is very useful once we do field investigations. For example, once we do a well test. So we technically use these transient solutions or simplify the steady state solutions to go to the field and measure the drawdown ourselves, and using knowing the drawdown here, we inversely solve the problem and find the for example, the storage coefficient or transmissivity of the aquifer. So technically these solutions are very important once we would like to go and find the characteristics of the aquifer, which is usually done under the well test concept. Okay, so I will stop here. Thank you.